Hello, everyone. Good afternoon. Looks like we're kind of light today, but that's okay. Lectures are posted online afterwards. Okay, so today we'll see if we can finish up this lecture, or at least the first part of the CMOS and signal integrity part of the course. And also there's just a reminder, there's a quiz out there, quiz 6, that is due on Monday before class. That'll cover this material. So hopefully I get through all this, so you'll be ready to take the quiz. So last time we were talking about devices, and nMOS and PMOS devices, and I showed this picture several times, this cross-sectional picture, and I also added this picture last lecture on Monday, this three-dimensional picture, which is nice because it shows that these transistors have a length and a width underneath the gate, which defines their behavior. It defines much of their behavior. The length is typically set to the minimum for the fabrication process, and then the width is normally set to be twice the length. So when you scale down the minimum feature size, you're scaling down both the length and the width at the same rate. I think that the oxide thickness tends to shrink a little bit too with more advanced fabrication processes as well. But generally, when you think of the new process, it's generally has to do with focusing on the length and width and scaling those down. Both the PMOS and the nMOS are basically capacitors, where the gate is one plate of the capacitor and the substrate is the other plate. But when you turn on the transistor by having the gate voltage exceed the threshold, it creates an inversion region in the channel, which are the minority charge carriers. When that inversion region is created, then the gate voltage is relative to the source. And the source terminal, of course, is one of the two terminals on either side of the gate, on either side of the transistor. The source terminal, sorry, I'm flipping around a little bit here. The source terminal is the side, by convention, is the side of the transistor that has the lower voltage for the nMOS and the higher voltage for the PMOS. And that's kind of hard to remember, but the source voltage, one way to think of it is that the source terminal is the side that is closest to the power supply rail. So in the case of the pull-down network with the nMOSs, the source is going to be closer to ground. And in the case of the PMOSs, the source is going to be closer to VDD. Now, when I say closer, I know that's a little vague. The reason I'm saying closer and not connected is because if you have, for example, a NOR gate, you have the nMOSs are in parallel, so each of their source terminals can be connected directly to ground. And this is going to become relevant a little bit later when we talk about the total capacitance. But the source terminals of these nMOSs in the pull-down network are just wired directly into ground. So obviously the source terminals here will be the lower, they'll have the lower potential. However, if you look at the PMOSs in the pull-up, they're connected in series. So the source terminal on each of these individual PMOSs is on the top, but it's not necessarily connected directly to VDD, but it is connected to a higher voltage potential. So you'd have, on this first guy at the top, you'd have source on the top, and then the drain, and then the source and drain, and then source and drain. So the drain of the bottom PMOS would be connected to the output. And then the drain of all three of these nMOSs would also be connected to the output because they're in parallel and the PMOSs are in series. Once the Go back again. Oh, sorry, where's that picture of the inversion layer? I like that picture. Once the inversion region rather, not layer, inversion region. Once the inversion region is established, then the gate voltage is relative to the source terminal. So VGS would be the voltage of the gate minus the voltage of the source. You can also have VGD, which is VG minus VD, and then VDS, drain source, is the voltage drop across the source and drain. Okay, now you might say, well, why is this important? Why is all this relevant? It's relevant because it has to do with the behavior of the transistor. The threshold, because the threshold is relative to the source, then when the voltage over the transistor exceeds a certain level, when I say over the transistor, I mean the source drain, or drain source. Sorry, drain source. When the drain source is high enough, it pinches off the ability for it pinches off the channel and makes the transistor saturate, so you can't continue to increase the current as you increase the voltage over the transistor. And so that's the whole idea behind the three different operating modes. So there's the cutoff mode, where the transistor is turned completely off because the voltage on the gate is less than the threshold. Now, technically, in the cutoff mode, you're talking about the voltage of the gate relative to the body, but but yeah, it's basically when you haven't reached the threshold, when the gate hasn't met the threshold. Now remember, for an nMOS, that the threshold is going to be, it's generally about 0.7 volts for an nMOS, and then for a PMOS it's negative 0.7 volts. So you have a negative threshold voltage for a P-type. Hopefully I said that right. P-type. The P-type is the negative threshold. The N-type is the positive threshold. And both are, the absolute value of both is typically about 0.7 of a volt. Of course, you can change that by changing the doping and I think the oxide thickness. There's ways that you can change that, but generally speaking, it's remained pretty consistent in most modern processes around 0.7, which is why you'll notice, if you look at your motherboard settings, and you buy your computer, you'll notice that you can't really drop the voltage, because modern motherboards have dynamic voltage scaling. You can change the voltage. Generally, if you want to increase your clock rate, you need to increase the supply voltage and the clock rate together. But you'll notice that you can't really go much below 0.8 or so, because you start to get close to the threshold voltage. Okay, so then there's the linear mode, which is when your your VGS, V gate source, is greater than the threshold voltage, and that's when you form you begin to form an inversion region under the gate in the channel, which is the minority charge carriers. And in the linear region, the current will increase linearly with the VDS, the voltage of the drain relative to the source. So as you increase the voltage over the transistor, the current will scale proportionally. That's linear mode. And then there's a saturation mode, which is when the VGS is greater than the threshold, right? But the drain source is greater than the gate source minus the VT, the threshold. So basically, when the difference between the gate source and the threshold is less than the total voltage drop over the drain and source, VDS, that's when you enter saturation mode. And so the problem there is that what's happening there is that the voltage of the gate relative to the source is fine, right? You still have a nice inversion region under that side, under that half. The problem is on the other half over here by the drain is at a higher voltage relative to the gate, and so it pinches off. You end up with a if you look at the voltage of the gate relative to the channel across the channel from the drain to the source, that voltage drop is still pretty good over here by the source, but it's very small over by the drain because of the big difference in voltage between the drain and the source. And so that's what creates this pinch-off effect, where when they say pinch-off, it's literally like pinching off. If you consider the channel to be the part of the substrate that has the minority charge carriers in it, the electrons in this case, then it literally just gets pinched off. You end up with an area on the right-hand side here with very little charge carriers, and on the left-hand side you have your charge carriers. So the effect of that is that it basically stops, it prevents you from continuing to increase the current through the transistor as you increase the voltage. So that's saturation mode. Okay, so we talked last time about we worked through the linear region equation that describes the current that calculates the current that flows from the drain to the source as a function of the gate source and the source drain and other factors as well, other parameters of the transistor. So I have I added a new slide here where, well, I forgot that was animated. Sorry. I added another slide here to try to break this down a little bit more clearly. So the current flowing through the whole transistor from drain to source is going to be the charge of the channel divided by the carrier time. And so the charge is capacitance times voltage. The capacitance is a function of the width and the length and the oxide thickness, as well, and then the voltage is the voltage. Well, the voltage on the channel it depends where on the channel you're at. So you have to then you have to say, voltage of the gate relative to the channel minus the threshold, but the voltage of the gate relative to the channel depends on where you are in the channel, as I mentioned, because you end up with kind of a gradient of voltage across the channel. So you can calculate the average voltage on the channel as the voltage of the gate relative to the source minus the voltage of the source relative to the drain divided by 2, and then you have to subtract the threshold voltage. And like I mentioned last lecture, that I've never really been very clear on why you have to subtract the threshold voltage from this voltage, but that's the only part about this that's kind of always been unclear to me. But obviously the channel voltage is pretty clear, but you have to back out the threshold voltage from that when you do the calculation. Now, as I mentioned, though, the threshold voltage is a constant. Generally speaking, speaking for a given fabrication process. And then, so you can then pretty much combine all this together, and you end up with capacitance of the oxide times width of the channel times length of the channel multiplied by the voltage of the channel minus the threshold. And then the carrier time is literally just the physical time it takes to move carriers. So that's going to be the length, because just to be clear, so you guys aren't confused on this, I'm going to go back here again to, this. So you have width and length, right? But the carriers are only traveling along the length. Now, as you increase the width, you get more carriers, so you get more current. But but whenever you're sending current from the drain to the source, you're just traversing the length, not the width, the length. The width just gives you more oomph, more carriers. But the actual time is the time they need to actually make the trip is calculated in terms of the length. I think that's why they call it the channel length. It's like the first to the travel length that the carriers have to travel. Okay, so then so the time would be the length divided by the velocity. The velocity is the mobility multiplied by the electric field. The electric field is just the voltage divided by the length. So that's a much simpler equation for electric field strength than I expected. You know, voltage divided by size, or length in this case. So that's pretty simple. So you end up, if you put all this together, the carrier time is L squared divided by mu VDS. Now you'll notice that there's an L actually in the numerator, right? And there's an L squared in the denominator. So obviously the L in the numerator is going to cancel out, and you'll end up with just an L in the denominator. So as I mentioned, like if you decrease L, then you're going to increase the current. But I also mentioned that the width is also scaled down generally at the same rate as the length. So the transistor, you'll shrink the length and the width together at the same rate. So so that kind of cancels out, right? Because you got a width, you end up with a width in the numerator and a length in the denominator. And so, yeah, you reduce the length by a factor of, whatever 7.75 or something like that for Moore's law typically. But you're doing the same thing to the width in the numerator. So what ends up happening is that the transistor shrinks and the current generally stays about the same. I mean, assuming that you're using minimal sized transistors, which means that you can fit the same amount of that you can fit more transistors on the chip, obviously, but for each individual transistor, the current stays the same. Now you might say, oh, wait a second, then that means the whole chip is going to take more power, though, because you're adding more transistors to the chip. And that's true. That wasn't always true. So there's this thing called Dennard scaling that basically said that the total amount of power per unit area of a chip is constant even as you scale down. And you might say, well, how that's possible if you're going to have more transistors and each transistor uses the same amount of power as the ones before? Well, that was because I think the reason was because the oxide thickness. So you see this C oxide was shrinking, and this is a numerator term. And so I think that was, the oxide, the oxide thickness was here, which was part of, that ends up being in the denominator. So how would that work? Well, it used to be that basically that you would actually save a little current. Well, you can also scale the voltage. Well, the point is that none of that still is in effect anyway. So this is why we have this issue of dark silicon and how you can't run all the transistors on the chip without exceeding the power envelope, because chips are becoming, the amount of power used per unit area is actually increasing now as you scale down the transistor sizes. So anyway, that's the point of this is it's kind of complex how these factors change as you improve the fabrication process. And then, you can always, as I mentioned last lecture, you don't have to use the minimum size transistor. If you want more current, then you can always scale up the width while leaving the length the same, and so you get, a linear increase in current as you increase the width. And so generally, if you need a powerful driver on the chip, because you need to drive a large load or a large fan out, then you can just make a bigger transistor. You can make an inverter with non-minimal width transistors, and that'll act essentially as an amplifier. Okay, so yeah, so this is the same slide I presented last time. This is basically just different ways to rewrite this equation. You'll notice there's this beta term. So this mu Cox width over length is collapsed into beta. Beta is a term that's used to describe the basically the width and length, and also the carrier mobility. You can also break beta out into k prime width length if you want to express it that way. But the problem with beta is there's two issues with beta. One issue is that the mobility, the charge mobility, is part of beta, and that means that and because the n-doped silicon typically will have twice the mobility as the p-doped silicon. So in order to keep the beta term the same, even in the same process, I'm not even talking about going from one process to the next. Even if you're designing one chip, within that chip, your PMOS transistors will have to be twice the width of the nMOS in order to achieve the same beta, the beta term, and that's because of the difference in the charge mobility. That's that mu term. Now, obviously, if you want to build an amplifier and you want to build a giant transistor with a larger width in order to drive more load, then that would also affect your beta as well. But the beta, the way that beta is represented typically is it includes both the charge mobility, and that is linked to whatever transistor you're building, as well as the width and the width-length ratio. And you never want to go anything. You never want to make the length larger than the minimum. But the width is something that you can manipulate that as someone doing layout. And I haven't showed any layout, but basically when you design a chip, you're actually drawing polygons that represent the different layers of the mask, the different layers of the chip, and so you can actually draw. You're literally drawing diffusion areas, and so and the diffusion areas in the channels, and so you can draw them however you want. You could draw a big transistor, but the rule of thumb is you keep the length a minimum, and the width is something that you can vary. You have a minimum width, which is twice the length, but if you want a stronger transistor, you make it wider. Okay, so let's see. So then there's the DC response of these transistors. So these plots are showing the current, which is on the vertical axis. It's the current versus the drain source voltage, and there's one trace for every gate voltage. So if the gate voltage is gate source voltage is 1.8, which is, I think the implication here is that 1.8 is pretty much VDD, right? That's kind of your max. You're giving it the full gate voltage. Then what'll happen is you'll be in you'll start out in linear mode, right? Because the gate source volt, there's no cutoff for this curve. There's no cutoff mode because you're above the threshold. This whole trace is above the threshold. So there's no cutoff mode. So what we're seeing is only the linear and the saturation. So the linear mode happens as you raise the drain source voltage up to about, I guess about 1.2 or so, and then you enter saturation mode. Does that make sense? Well, how do we know if it makes sense? Well, we know it makes sense because if you take 1.8 and you subtract it from 1.2, which is about the point where you go into saturation mode, the answer is about 0.6, right? And 0.6 is about what the threshold is, right? I said 0.7. It's 0.7, 0.6, 0.6, 0.7, somewhere in that neighborhood, right? So what's happening is that the saturation mode is hit at 1.2 volts, which is significant because that is 0.6 volts away from the gate source, right? But if you drop the gate source to 1.5, the linear mode is more or less the same, except you enter saturation at, well, it's basically going to be 1.5 minus the threshold, which is 0.6, I guess, in this case, so about 0.9. So yeah, there you go. Once you get to about 0.9, you enter saturation mode, right? And so if you have a 1.2 gate source, it's going to be 1.2 minus 0.6 about 0.6 volts, right? There's your saturation point, and so on. So basically, you want to have the gate source voltage as high as possible in order to delay saturation mode for as long as possible, which is why these chips are, that's why they're binary, because you basically, your gates, ideally your gate voltage is always going to be binary. It's going to be 0 or it's going to be VDD. And so yeah, generally speaking, you want to keep the gate voltage either all or nothing, essentially. Now you might be wondering why the linear mode, why is this linear mode, why aren't the linear modes all on top of one another? I don't know. The slopes on linear mode are slightly different depending on your gate voltage, which is a secondary effect. I've never looked at that. But I mean, ideally linear mode is just linear, right? It should just be it should have a slope of 1. But clearly, you know, as you lower the gate voltage, the slope changes even in the linear mode a little bit. It has effect on the linear mode. And then PMOS is similar, except in this case, the gate source voltage is negative because the threshold is negative, and also the VDS is negative. And why is that? And the current is negative too. Well, that's because of the convention. If you go back and you look at all the way back to here, notice the PMOS has the source on the top and the nMOS has the source on the bottom. So if you're going voltage of drain to source, it's going to be positive. Voltage for nMOS, voltage to drain to source on a PMOS is going to be negative, right? Because it's opposite, right? Drain versus source. Likewise, voltage of the gate versus the source will also be negative because the source is going to be connected to VDD, basically. So if the gate is anything less than VDD is going to give you a negative voltage on the gate, and then the voltage of the drain versus source is going to be negative, and then the current from the drain to the source is also going to be negative because you're measuring the current from this bottom terminal to the top terminal, so it's a negative current because the current obviously is flowing from the power supply down. So the current is flowing from source to drain, but if we express it in terms of drain to source, then we're going to have a negative number there. And so that's why you're seeing that weird negative plot. That's the reason. It's just because of the convention in terms of what you label the source and the drain. Okay, so now why is this important? This stuff is important to understand how logic gates work. So if you consider an inverter, which is the simplest type of logic gate, so it has one transistor, has one input, and so it has 2 transistors, has one pull up, one pull down, and they're just connected very simply. You know, they're basically the nMOS and the PMOS are connected in series, and so the V-in is going to be connected to both gates. So in terms of the gate, like if this is a logic gate and we're trying to figure out if we want to solve how the V out changes as a function of V-in, the V-in would be connected to both of the gates, and so the gate source for the N, so GSN, this would be the GSN, the gate source nMOS, would be the input, right? So VGSN is equivalent to the input. The VGS, actually we don't have the P here. Oh yeah, this is just for the N. Oh yeah, right, this is, the next slide is the P, right? So this is just the nMOS, right? So the VN is the gate voltage for the nMOS, right? So that's, again, VN versus the source terminal is going to be in. Then the output is going to be connected also to the nMOS, but it's not connected to the gate. The output of the gate is connected. Oh, that's confusing. The output of the the output of the inverter is not connected to the gate of the nMOS transistor. It's connected to the drain. So the drain source voltage of the N is going to be V out, right? And that's it. So in cutoff mode is, if your input to the inverter is less than the threshold, then you're in cutoff. If the input to the gate is greater than the threshold, right, which it would be in both linear and saturated mode, see, GSN is greater than VTN. That's true in both cases. The difference, though, between linear and saturated is if the gate voltage minus the threshold gate source, if that's greater than the drain source voltage, right, then you're in linear mode. If it's less than the drain source voltage, you're in saturation mode. Okay. Now you might say, wait a second. What is the drain source voltage? The drain source voltage drop should be negligible, right? Because the drain is at VDD, and the output is, if you're in linear or saturation mode, you expect the output to be basically at VDD as well, right? Right, because you're turning on that's the definition of turning on a transistor, is you're basically connecting the output to VDD. If you're pulling up, that would be the PMOS. But let's talk. We're talking about the nMOS here, so let me focus on that. So if you have the output, if the nMOS rather is the pull down, and you're pulling down, you turn that on, you want to connect the output to the ground. So you expect that the voltage drop over the nMOS should be pretty small, right? I mean, you expect there to be ground here and ground there, right? So, why would you ever be in saturation mode? That doesn't make any sense. Well, it turns out that you will be in saturation mode depending on the switching. It happens when you switch the transistors, when you switch the output. So when you go from off to on and on to off for these guys. So I'll talk about that here in a second. Let's take a quick look here at the PMOS. Same idea. The gate source is going to be, we're looking for that to be less than the threshold. Why less than? Less than because, remember, it's negative. So if the gate source voltage, and again, the source terminal is now on the top, right? So if the gate is the gate source is going to be negative, and if that negative value, if the absolute value of the negative value is greater than the threshold, which would be the same as saying if the value of the gate is less than the threshold, then we go into either linear or saturation mode. And then we determine the difference here between these two guys is if the gate minus the threshold, the gate voltage minus the threshold, if that's less than the total voltage drop drain source, right? So again, these are all negative values. So you'll notice that in linear mode, the voltage is less, the gate voltage minus the threshold is less than the total drop across, right? In linear, and it's greater in saturation. So greater meaning that you're pinching off, right? Because if the voltage of the gate relative to the source drain voltage is less, it's the voltage of the gate relative to the drain ultimately that's determining this. But if that goes too small, then you pinch it off, right? Okay, so like I said, we want to figure out what is the output of this gate versus the input. How do we calculate the curve, the trace? How do we simulate this transistor, basically? How do we model the transistor? So I mentioned that ideally we would be in either cutoff or linear mode, right? That's how these transistors are meant to operate if we're trying to use them as switches. But the problem is that when you're switching the gate, you also enter into saturation mode as well during the period that you switch. So so how do we figure that out? Well, basically, it's actually trickier than you might think. So the way that this is done is you actually solve well, you're solving Kirchhoff's current law, which if we assume, now this is a little bit misleading because we're assuming for the moment that there's no current coming out of this transistor. So we're assuming that we're not loading the output. If we're not loading the output, if there's no current coming out of this guy, you know, which would happen if we had like a load, if we had a resistor on this guy to ground, or a capacitor attached to the output, which is what you would have if you were driving other gates. But if we simplify this and we assume there's no outgoing current, then we basically just have to balance the current going through these two transistors, right? So the amount of current coming out of VDD through the top transistor should equal that, the current going down through the bottom transistor. Okay, so the way you go about doing that is, now remember, let me back up here a minute. So the goal is to look at the voltage of in versus the voltage of out, right? So I can change the voltage of the input, but how do I use that to determine the output voltage? Well, you don't really know the output voltage, at least not right away. So one way to figure this out is to basically solve the current for various voltages. So you kind of discretize the problem. So you basically choose, in this case, I'm going to choose 5 different voltages that I'm going to put as the input. VN0 through VN4. And for each of those, I am going to basically sweep the output voltage, which would be, you know, the current, the source drain current, sorry, the drain source current for both the nMOS and the PMOS. The nMOS is shown in green, the PMOS is shown in blue. Okay, and then I will figure out the current. Now you might say, how do you know the current? Well, it's the equation. You just solve that, you solve this equation. Right? This equation will give you the current, assuming, of course, you know beta, and so you have to have a certain, you have to have technology parameters in. So beta has mobility and oxide thickness, and then of course you have to know the size of the transistors with width and length. So you need beta, but if you have beta and you know the gate source, which is, you know, these values, gate source, and you know the drain source, which is what I'm sweeping, right? This is the drain source. So I've got all the information I need to calculate the current. So I just get the current. I just plot the current versus drain source voltage. And then for each of those input gate voltages, I check to see where the lines intersect. So where does the current flowing through the nMOS match the current flowing through the PMOS? And wherever they match, that's the true voltage, the true Vout voltage. For, you know, both, obviously both you're going to get different voltages. So these lines will meet, right? Wherever they meet on the vertical axis, but then the voltage of the PMOS and the nMOS will then be different for each of those meeting places. So I'll find the intersection here, and I'll find the corresponding intersection over here, and this will tell me both voltages. Okay, so let me show you how that works. I have some neat slides. Now, one of the things that I think is kind of confusing here is, let me back up here a minute. So notice this plot. This plot shows the voltages of the PMOS being negative, as they should be, and the currents being negative, right? But the problem is if I show them that way, I can't figure out where they intersect. It's harder to find intersecting points. So instead, when you look at this plot, blue lines are actually kind of done, it's a kind of a mirror image, because the vertical axis represents the absolute value of the current flowing from drain to source on the PMOS, right? So that just flips this brings you from the negative voltages to positive, right? However, one thing that's not shown in this plot is the fact that the horizontal axis is also switched. So you start, so this is a little misleading because it says VDD over here, and it says V out with an arrow pointing from left to right, but that's actually for the nMOS. For the PMOS, you're actually, the horizontal axis is labeled from negative VDD to 0. So, and again, I mean, you can tell that, right? Because, VN, well, it makes sense, right? Because why would the current be so high at 0? It's 0 volts, right? It doesn't even, like, if you look at that blue line, the blue line indicates at 0 volts, you got all this current, right? Well, that doesn't make, why would that be? Well, the reason why that is because that's not 0. That's negative VDD. And so then as you increase the voltage from the VDS for the PMOS, you decrease the current, right? So basically, as you increase the voltage from negative VDD to 0, you start out in saturation mode, and then you switch to linear mode, and then you basically go to nothing. And you don't go to nothing because you go to cutoff. You go to nothing because the voltage hits 0, right? So once the voltage is 0, the current is 0, even if you're not in cutoff mode. So you can still be in linear mode and have zero current through this guy. Okay, so yeah, so we do that for 0. Let's see. 0. Vn is 0. So 0 would be basically, if your input is 0, that means the PMOS is seeing negative 1.8 volts or negative VDD volts on the gate source. Then 20% of VDD. So I start bringing the voltage up, which means that this will no longer be negative 1.8. It's going to be 80% times negative 1.8, whatever that is. And so that'll bring down, actually it'll shift the saturation point to the right, and it also will decrease the total amount of current that flows through even when you get into linear mode. And then 0.4 VDD, increase the voltage a little bit more, and so on. Now, as you, at some point, sorry, let me go back here. Sorry. At some point, once you hit 0.4 VDD, let's see, 0.4 times 1.8 volts. So you're getting close to the threshold now of the nMOS transistor, right? So the nMOS transistor is now transitioning out of cutoff at this point. So this is interesting because you can see that the both transistors are either in saturation mode or linear mode in this operating regime. When the Vn is 0.4 VDD, they're both on. Technically, they're both on. Now, what does on mean? Well, on means they're either in, they're either in linear mode or cutoff, or linear mode or saturation mode, depending on the voltage over their source and drain terminals. But neither transistor is off. Neither one of them is in cutoff mode anymore. So they're both on, but they're just both on to different degrees. Because of that voltage is 0.4 VDD. We're kind of 0.4, right in the middle. I mean, we're in the middle, right? You're instead of giving it a 0 or 1, you're basically giving the gate a half, right? Essentially. So both transistors are on, and you can see that the PMOS is basically in saturation mode for most of that, as is the nMOS actually. But the nMOS is in linear mode over here, and the PMOS is in linear mode over here. Okay, so then basically at that point we can see that, well, there's an intersection point right here, right, where the current is equal. So basically what that means is, because there's an intersection point here, you can see that at 0.4 volts of the now remember, we're talking about the inverter. So when you have an inverter and you hit it with 0.4 times 40% of the VDD voltage, you can see that the V out would be right there. That's what you would actually be putting out. Okay, so then you do that for the different values. What you end up with is something that looks like this. You have these intersection points, and then you can see that if you take each one of these points, you can see, and actually I'm sorry, each point on this curve represents actually just one point, on one intersection point. I misspoke earlier. You're not looking at both, because the V out is actually, the V out is the, well, so wait, let me rephrase that a second here. So remember I said the V out, this horizontal axis is 0 to VDD for the nMOS, and it's reversed for the PMOS. So so technically each point is we're just concerned right now with just V out for plotting this, which is the output in this case of the nMOS drain source voltage. So at each one of these points, you can also plot the corresponding point on this curve. So what you end up with is a curve that will plot each value of V in to a corresponding value of V out. So basically, you're looking for each one of these, for each one of the V ins, you're looking for the intersection point that will give you the V out, the corresponding V out. Now you might say, okay, now I'm starting to see that you're basically characterizing the gate, right? You're looking at the shape of the output and the transition. So what is the point of all this? Well, hopefully you're starting to see that the point of all this is that we're measuring the performance of the gate. We're starting to get a picture of how fast the chip will run, essentially. Now this is just internally inside the gate. We're not considering other factors yet. But this is the shape of the output of the inverter. Okay, so you can see that with the Vn, when you start out at 0, obviously, so you're putting a 0 in. What's that doing? It's going to turn on the PMOS, the pull up. It's going to turn off the nMOS. The nMOS will clearly be on cutoff, right? Because you're essentially giving a 0 to an nMOS. That's a cutoff. The PMOS is in linear mode. And you might say, why is it in linear mode? I mean, shouldn't it be in saturation mode? No, it's actually in linear, because as I mentioned, the gate voltage in this configuration way over here, the V out is going to be pulled up really hard to VDD. So V out and VDD are basically going to be, basically equal or very close to one another, which means the difference between the source and drain voltage is essentially 0. So that Vn is going to look like a real nice, strong value on the gate in terms of the difference between the gate source versus the drain source, right? So as a result of that, we're in linear mode. We don't get to cutoff until the gate source and the gate and the drain source become equal, basically. So that's linear mode, right? Now, once we start increasing the input voltage, at some point the input voltage is going to hit the threshold of the nMOS. Well, now we've got well, not a problem, but we start to see some weird things happen, because once that happens, the nMOS is going to switch into linear mode. I'm sorry, it'll actually, sorry, scratch that. The nMOS will actually be in saturation mode. And the reason for that is because the drain source voltage of the nMOS will be very high. The V out will still be, it'll still be getting pulled up. You see, it's up, right? The output is high. Whoops, sorry. The output is high, right? So the inverter is actually generating still a high output voltage. And so the input to that nMOS is going to look small compared to the voltage that we're dropping over the nMOS, which is why it'll be in the saturation mode. The PMOS, on the other hand, will still be in linear mode because, again, the V out, the drain source voltage over that PMOS is small, right? Because we're still pulling up the output. So we're pulling up the output, and we got the other side of the PMOS connected to VDD. So his drain source is very small compared to the gate voltage. So that's why we're still in linear mode. So we got linear mode on the top, and we got saturation mode on the bottom. Okay, then we get to the middle where the VN is half. This is kind of the crazy part, right? Where you're setting the input voltage in between 0 and 1. So it's like half the power supply. So VDD divided by 2 is our input. Now both transistors are going to be in saturation mode because you're dropping a huge voltage over both compared to the input. And so basically, you don't, that's the kind of the thing, you don't want that to happen, right? You don't want them both on, because that's essentially what's happening. Not only are both transistors on, but they're in saturation mode, which means you're getting the most current you'll ever have flowing from VDD to ground. This is dynamic leakage current. And you might say, well, you just don't do that. Well, you have to do it at some point. Whenever the transistor switches, you're going to have to be in this state at least for some amount of time, right? You're going to be in saturation mode in both transistors. And this is where you lose power. This is why, your cell phone battery is going to die, after a day or so, is because you switch this guy and there's a time when both transistors are in saturation mode. And it's unavoidable. And then once we get the VDD, the VN above VDD over 2, that'll put the nMOS into linear mode, because we're going to start pulling down the V out, pulling it down closer to ground. Meanwhile, we still have above threshold voltage on the PMOS and a big voltage drop between VDD and V out, because we're pulling the output down, but yet the PMOS is still seeing this huge drain source voltage drop, and so the PMOS will then be saturated. So there'll be a time when the PMOS is saturated and the nMOS is in linear mode, until eventually, once the voltage in gets high enough, we'll just end up cutting off. The PMOS will get cut off, and the nMOS will be in linear mode. Linear mode being that it'll be nice and happy in linear mode because its V out and its other terminal are both basically equal. Source drain voltage is 0, and the VN is above the threshold. So that's linear mode. So that's how these things work. Okay, so again, we're doing all this to study the performance. So what sort of performance metrics are we talking about here? We're talking about delay. We're actually two things. We're talking about delay through a gate, and we're also talking about the rise and fall time of the gate. So those are the two main metrics you care about. So there's the time for the propagation delay. So if you have your input and you've got your output, the propagation delay is measured from the time the input crosses the halfway point to the time that the output corresponding to that input crosses its halfway point. So in the case of an inverter, we want to measure the time from the halfway up from 0 to 1 to the halfway down from 1 to 0 on the output. And that's the propagation delay, and that's the falling propagation delay. And then likewise, there's a rising propagation delay, which is when we drop the input and causing the output to rise. And so there's a delay between when the input crosses the halfway point as it falls and when the output crosses the halfway point when it's raising, and that difference in time is the propagation delay rise time. And then the average propagation delay is just the average of the rising and the falling. You'll notice that it takes longer. Well, actually, it looks about equal, doesn't it? In my experience designing chips and doing simulations, transistor level simulations, usually the rise time is a little slower than the fall time. Why? Because the PMOS charge carriers are not as good. So typically, you design the PMOSs to be twice the width in order for the beta terms to be equal, but usually that's not quite good enough, because the mobility is between 2 and 3 times less on the PMOS. So if your PMOSs are twice the size of your nMOSs, you're going to see when you simulate your circuits that the pull-up time, which is the rise time, is usually a little longer. Okay, but that's not necessarily reflective in the propagation delay. So the propagation delay, rise propagation delay may still be okay, but the time it takes to actually get the signal up can be longer than it takes to drop it. So yeah, let me clarify that. So the propagation delay is the input to output delay of the gate, whereas the rise and fall time is the time it takes the signal on the output to go from 80% to 20% of VDD. And so what I was referring to there was the rise time is usually a little longer for the for the gates than the fall time because of the not quite perfect sizing of the PMOS transistors relative to the nMOS. But the propagation delay, rise propagation delay, that might still be equal. I'm not sure. I don't remember the rise propagation delay being longer than the fall propagation delay. I just remember, when you look at the traces, it's usually the slope is usually a little less on the rise time. Okay, and then the other metrics are, there's this thing called contamination delay.
Can we look at the rise and propagation delay for a second? Why is
the propagation delay is the worst case delay, whereas the contamination delay is the best case delay. So basically, if you have a given gate, there is the minimum amount of time it'll take to propagate a signal versus the maximum. Now you might say, why in the world why would there be a difference? Well, because actually there's a very simple explanation to that. So if you look back at our, sorry, I'm switching back and forth a lot. I'm looking for, yeah. If you look back at this NOR gate, notice that there's 3 PMOSs in parallel here, right? Now, in the case of a NOR gate, now keep in mind, I'm not talking about an inverter here. So in order for this contamination delay to not equal the propagation delay, first of all, you have to accept the fact we're not talking about an inverter. Inverters probably won't have a difference between propagation and contamination. But if you have a gate like a 2 or 3 input gate, like take this 3 input gate, what happens if I set all 3 inputs to 1 all at the same time? Well, what that's going to do is create 3 parallel connections to ground, right? As compared to switching only one of these inputs to 1 and leaving the other 2 0. Well, if I do that, I'm only going to turn on one nMOS. So the question is this gate going to be faster if I set all inputs to 0 at the same time versus just have all inputs be 0 and, sorry, let me repeat that. I think I said that wrong. Is it going to be faster if I set all 3 inputs to 1 because these are nMOSs. So if you set these to 1, they're going to turn on. So if I set all 3 of these to 1, I'm going to pull down with 3 parallel paths to ground at the same time. So I'm going to give it 3 ways to drain current through down to ground, as opposed to starting out with A, B, and C 0, right, and just setting one of them to 1, right? If I just set one of them to 1, like I go from 0, 0, 0 to 0, 1, 0, that will just turn on this middle nMOS. And yes, the output will still be pulled down to ground, but it's only going to have one of these transistors pulling it down to ground as opposed to all 3 of them pulling at the same time. So the reason why the contamination delay is different from the propagation delay is because it depends on the inputs. Certain input changes will cause a faster transition depending on which transistors in the pull up and pull down networks are activated and how many paths you get to power and ground, if that makes sense. So the contamination delay is, there's a rising and a falling contamination delay. It is a delay. It's from input to output, but it's the shortest amount of time you can expect to wait versus the propagation delay, which is the longest amount of time you can expect to wait. And it's based on which inputs cause the gate to switch. Certain combinations of inputs will cause the gate to switch faster because of the parallel and serial nature of the pull up and pull down networks. Hopefully that makes sense. Okay, so the last thing I want to talk about is how do we actually calculate the delay? Okay, so we come back to this picture, of a of an NFET or nMOS on the left, a PMOS on the right. I mentioned that there's a diode formed between P to N. P to N is a diode. You can't send current from N to P, because if you have a positive voltage on N versus the P, that will make the diode reverse biased and no current will flow. There's a reverse biased diode. No current flows. However, the one thing I haven't mentioned about diodes yet is that a reversed biased diode doesn't send current, doesn't transmit current, doesn't conduct current, but it makes a wonderful capacitor. So what you end up with is a capacitor between the diffusion areas and the substrate, or the well in the case of a PMOS. Reversed biased diode, which is the diffusion area to the substrate, is a capacitor. And of course the gate to the substrate, also a capacitor. In fact, that's supposed to be a capacitor. That's the way it works. So this capacitor is unavoidable, because if we didn't have a capacitor for the gate, if the gate wasn't a capacitor, the transistor wouldn't work. But the capacitor that's also formed between the diffusion areas, which is the source and drain, to the substrate, that's called a parasitic capacitor, because it's a parasite. We don't want it. We don't want that capacitor. It hurts us, slows things down. But there's no way to avoid it, because a reversed biased diode is a really good capacitor. Doesn't send current, but it acts as a capacitor. Okay, so as a result of that, you can model a gate, or you can model a transistor as a switch in order to simplify its behavior, right? But even if you do that, you need to consider the fact that there is a capacitor formed from the gate to ground in the case of an nMOS, or from the gate to VDD in the case of a PMOS. But the point is, there's a capacitor. It doesn't matter if the capacitor goes to ground or VDD, it's a capacitor. So there's a capacitor on the gate. There's also a capacitor on the source and drain. Now that capacitor, the capacitance is going to scale with the size of the gate. When I say size, I mean width, because remember, length is always minimal, but we can vary the width. And in fact, we do vary the width, at least for the PMOSs. They're supposed to be twice the size of the nMOS. Okay, so there's this value K. So each transistor has a size, which K, and again, K is the width, but it's in units of the length usually. So like, for example, if K is 1, that means your width would be twice your length. If K is 2, that means your width is 4 times your length. If K is 3, that means your width is 6 times your length, right? But that's not important to know. I mean, the important thing is that K is basically the size of the transistor, which determines the capacitance. So generally speaking, the capacitance of the gate is about the same as the diffusion areas, but the gate and the diffusion areas scale up with the size of the transistor. So a K-sized transistor will have K times C for the gate and the diffusion capacitance, right? However, the resistance of the transistor when it's on is half. Why is the resistance half? Well, it all goes back to that equation, the current equation. So if the width, which is part of the numerator, is twice, if you double that, you're going to double the current, right? So basically, so it's like if you're doubling that, you're doubling the current. It's as if you had decreased the resistance by a factor of 2. Because that's what happens when you have a fixed voltage and you reduce the resistance by a factor of 2, you double the current, according to Ohm's law. But in this case, it's not really Ohm's law, it's the IV characteristic of the transistor, but effectively, the effective resistance is going to be halved if I double the size of the transistor, right? So that's why we say the resistance value is scaled up with K as well. So the resistance of a nMOS is going to be basically R divided by K, and the capacitance of the gate and the two diffusion areas are going to be K times C. So C is the unit capacitance, R is the unit resistance, and we can change that by changing K, and of course K is just the width of the transistor, right? So for the PMOS, it's a little different though, because the resistance, again, because of mu, which is also in that IV, the charge carrier mobility of the PMOS is only half of that, which halves the current, which also halves the effective resistance. So that's why it says 2R divided by K. So generally speaking, the K value of the PMOSs are going to be 2 at a minimum, and the K value of the nMOSs is going to be 1 at a minimum. Okay. All right. So what is all the point? The point of this? The point is then we can then calculate the delay of one gate with a certain size transistors driving another gate with a certain size transistors based on the idea of using the delay term, the RC delay. So the RC delay is you take the resistance, you multiply it by the capacitance, and that gives you a time constant. It gives the amount of time it takes to either charge or to discharge the capacitor, the capacitance. Now you might say, where the heck did that come from? That seems awfully simple. It actually, I didn't put the derivation in here, but the derivation is the textbook I used for this has a derivation for this RC constant, and they do it using S domain. They actually write the transfer function like we did in the control theory part of the course. They use the transfer function, and then they do the S domain to time domain using the eigenvectors, or the eigenfunctions like we did. And then from that, they calculate the time it takes to drop or to raise. So they basically calculate the S domain equation of this RC network, and then they do a inverse Laplace transform, and that's how you get but the point is that we don't have to do that, because the result of that is that the time it takes to discharge or charge the capacitors, or to change the voltage, I should say, in the RC circuit is simply R times C. But the trick is figuring out how much C and how much R you have. And that depends on the size of the transistors, and it depends on what kind of gate you're using, and it depends on what you're driving, what the load is. Okay, so check this out. I think this is pretty neat. So like, look, this is the nMOS and this is the PMOS. This is where we go from the transistor symbol to an RLC circuit, switch level. Now you'll notice that the switches, there's a switch here that represents whether the source and drain are connected. So this switch is supposed to represent whether the transistor is in cutoff mode or if it's in linear or saturation mode, based on whether the thing is on or off. You got the gate capacitor, and then you got the two source and drains. Now you might say, well, that's pretty simple, right? Well, it gets a little bit more complicated, because if this transistor has a source that's connected to ground, right? Now you might say, well, aren't they all connected to ground? No. Actually, it depends on the gate, right? If you have a gate like, remember I have to keep going back to this. I like this. Yeah. So over here, you'll notice that all three of these nMOSs have their source connected to ground. But if we had these connected in, what if these guys were connected in series, like the nMOS is here? And that would be the case if this was an AND gate. If this was an AND gate, these guys would be in series, in which case only one of the nMOSs would have its source connected to ground. So you might say, well, who cares if it's connected to ground? What's the significance? Well, if the source is connected to ground, then you can disregard that capacitor. This capacitor wouldn't do anything if both sides of the capacitor were grounded, right? So keep that in mind. If this capacitor is only going to contribute in effect if one side is not, if you have at least one side not grounded. Makes sense? Likewise, with the PMOS, if its source is connected to VDD directly, then we can disregard that capacitor. Then we just have to consider the drain capacitor, right? So keep that in mind. Okay, so let's look at this example now. We've got two inverters. Now I know this looks kind of complicated, but just bear with me here a second. It's actually not that bad. If you have two inverters, you got the output of one inverter gets fed into the input of the other inverter. You've got this equivalent circuit. So if this first inverter is pulling down, then everything that's past this switch we can drop. We drop it, right? Why? Because we're pulling down. This switch is closed and that switch is open. So because that's open, because we're pulling down, the output of the first inverter is a 0. We drop all that, and then we go over to here, and also notice that this capacitor down here, this guy, is also dropped because both sides of him are connected to ground. So we drop this guy, and we drop these guys. So what you end up with is this 2C, that 1C. So you've got a C, you got the resistor from the driving pull-down transistor, and then you've got the load, which is the 2C and the C. So basically what you've got is the resistance from the pull-down nMOS, and then you got the source and drain diffusion capacitors, and then you got the gate capacitors of the transistor that's being targeted. So basically what you have is 1 R and 1 unit of R and 6 units of C. So basically your propagation delay is R times 6C. Done. That's all you got to do. Now obviously that's the pull down, that's the falling propagation delay, right? Now the rising propagation delay would be a little different because we would have to consider, we'd have to turn this guy off and turn this guy on. So the rising might be different. Also notice that the reason these are 2s are because we're assuming that the pull up is size 2, and I just noticed a bug. No, that's right. No, this is still R because it's 2, right? So these are 2. Sorry, scratch that. Yeah, these nMOS, the PMOSs are 2C, but only R, 1 R for the resistance because of the, because you have to double the size of the PMOS in order to get 1 R unit of resistance. Okay. All right, so let's look at another example. This is a 3. I got to speed up a little bit because I'm running out of time, but this is a 3 input. What kind of gate is this? Well, if you want to answer that question, you got to look at the nMOSs. The nMOSs have to be 1, 1, 1. So all 3 inputs have to be 1 in order to get a 0. Any other combination of inputs will give you a 1. So what gate gives you a 0 on a 1, 1, 1 input? Well, that's a NAND. Oh yeah, well it says NAND up there too on the title of this slide, but it's it's a NAND by looking at the nMOSs, and you recognize that all 3 inputs have to be 1. The only input combination that will give you a 0 output is a 1, 1, 1. And that's what a NAND, that's how NAND works. Because an AND gate is exactly the opposite. The only input combination that gives you a 1 is a 1, 1, 1. Okay, anyway, so now I'm gonna go a little fast here. Hopefully this isn't, I don't lose you guys, but notice that the nMOSs here, the nMOSs are 3 and the PMOSs are 2. Now you might say, well, that contradicts what you said earlier. You're supposed to have, your PMOSs are supposed to be twice the width of your nMOSs. Yes, normally that is the case. However, the reason why they're different here is because the PMOSs are in parallel, which means if we turn any one of those on, we see an effective 2 units of PMOS to VDD. But the nMOSs are in series. And so in order to get an equivalent resistance in our pull down as our pull up, you need to make sure that the nMOSs are actually bigger, because this will give you, having these be 3, it means that the resistance of each one of these is R divided by 3. And if you put all of those in series and you add up the resistance, you get a R, right? Meanwhile, the resistance to VDD, if any one of these PMOS is on, is going to be also 1 R, because of the fact that you have to have the PMOS double sized in order to get the equivalent resistance of an nMOS. Okay, so I know I went through that fast, but basically the bottom line is we're balancing the resistance of the pull up and the pull down. Okay, I tried to write that out too on that slide. Okay, so now if you put your capacitors in, so I got to put in all the capacitors for these guys. Diffusion capacitance and gate capacitance. This is all of them. Now, I know it looks kind of crazy, but it's not really that complicated. It's literally just you add a capacitor for each gate, you add a capacitor for each source and drain. That's it. The capacitors for all that stuff is to ground for the nMOSs, and it's to VDD for the PMOSs. That's all you're doing. However, you can simplify this. So this third diagram is the simplified version, where notice that this capacitor that has both terminals connected to ground, I'm just dropping it. It's redundant. Also, notice how the inputs have 3C capacitance on the inputs of the nMOS and another 2C gate capacitance for the PMOS. So, just combine them together. So 5C capacitance on each of the inputs, that represents the combined capacitance of the P and the nMOS. Remember, in a gate, you always have every input to every gate is connected to two transistors, one pull up, one pull down. So we have 5 units of capacitance for each of the gates. And then these guys, these nMOSs in series, we're going to have a 3 capacitance for the diffusion capacitance, but only 2 of them. Well, actually 3 of them. But these 2 are 3C, 3C. The one on the bottom gets dropped. And the one in the middle that's on the output, well, this one is going to be the drain capacitance of the topmost nMOS, and the source, and the drain capacitance of all 3 PMOSs. So you take 3 plus 2 plus 2 plus 2, that gives you 9. So there's a 9 total. Now you might say, wait. The 3C is to ground. These guys have a capacitance to VDD. Yeah, but it's still capacitance. It doesn't matter. It doesn't matter what the other terminal is connected to. As long as the one terminal is connected on the common net, then it acts like one big 9C capacitor. Because the capacitor is going to resist change to either VDD or ground. Okay, so really fast. I'm running a little bit behind. I want to talk about last topic is Elmore delay. I'm gonna go through this fast because I think it's pretty self-explanatory if you look at the slides. So Elmore delay is a way to measure the RC delay of a tree, where the source of the tree, the root of the tree is the voltage source, and then you can calculate the delay out to all the leaves of the tree. If you have an RLC network, it's pretty straightforward how to do that. For example, the delay would be R1 times C1, right? Because that's the first resistor and the first capacitor. But then you've got R1 plus R2 gives you a path to the second capacitor. So R1 plus R2 times C2. And then you have R1 plus R2. So basically, the resistance, you have an equivalent resistance to each capacitor. And when you have a lumped network like this, you add them together. So you add together the resistances to get to each capacitor, and you multiply it by that capacitance. You add all those together, and that gives you the total delay. That's called the Elmore delay. Now you might say, why do we need to calculate that? Because if you go back to the example that we had with the 3-input NAND gate, you have to use the Elmore delay in order to calculate the propagation delay for the rising and the falling through each of these complex gates. So basically, the rise time is going to be, you consider that the pull-ups, you pull up, right? So in this case, the pull-up is going through 3 parallel, wait a minute, was there 3 parallel on the pull? No, they were in series on the pull-up. The parallel was the pull-down. I just noticed that. Yeah, and the pull down was, oh, right. So sorry. Yeah, the pull down was here's the pull down. So you got the 3 resistors in series, and then you got each of the capacitors, and then you can calculate the Elmore delay from that for the pull down. So in this case, I'm going to start with the pull down. So you've got 3C. Let's see, where is it here? Right. So you've got a NAND. So you NAND gate driving H other NAND gate. So the H refers to you have to multiply the load capacitance, so the gate capacitance of the things it's driving. So basically, you remember you had 9C here on the output, right, of the gate that we calculated, and that was going to be from the output. Right, that's the output of this gate. But then you have the inputs. So the input capacitance is going to be 5H because there was 5 total units of capacitance on each of the inputs. So that's assuming that this guy is driving 1 input each on these H copies. So it's not like you're fanning out to all the inputs, right? So that's the total capacitance here on this leg. Okay, makes sense. And then we've got, let's see, then you still have, of course, the 3C and the 3C, the 3C and the 3C down here, but each of those are going through resistors. Remember that each one of these guys, when you're pulling down, gives you a resistance. So that's why you need the Elmore delay, because you have from the output, you go through one resistor to get through the first series pull down, and then another resistance, and then a capacitor, and then a third resistance. So that's where you're basically, you're adding up. This is the first guy, R/3. It's the first transistor. Then you go through the second transistor is R3 plus R3, and then the third one is R3 plus R3 plus R3. And for each one of those, you multiply by the capacitance at that net. So the capacitance on the first net is, I'm sorry, you're starting from ground rather. Sorry. I was going from output to ground. You start from ground because from ground you go through 1 unit of resistance here to a capacitor. Then you go through 2 units of resistance, and then the second capacitor, the 3C, and then 1, 2, 3 till you finally get to the output. So basically, you start from ground and you work your way up to the output of the transistor. And then, in the case of the VDD, you go the opposite way. Except the only problem with that is I don't remember why they're going through from VDD. Oh, I see. Right, because actually, no, sorry, I scratched that. See, you're only going through 1, actually. You see the Y? Yeah, I just looked at that wrong. The Y is the output. Notice you're only going through 1 transistor, right? And that's because the pull-ups are in parallel. That's why, right? Yeah. So you've got that there. Yeah, so you start with that. So you basically, these guys are disregarded. You see this R/3, R/3. So the only thing you count is the top resistor and then the output. So that's why you only have 1 term here. So it's 9 plus 5H is your, RC. So that's RC and times 9 plus 5H, right? So that's the pull-up propagation delay. Okay, and then finally, one last thing, contamination delay is the same thing, except this is what I was talking about earlier. If you turn all 3 of these guys, these pull-ups on at one time, then the effective resistance there is R/3. See that? Because you got 3 parallel resistors. So the only difference between the contamination and the propagation delay, it's only for the pull-up. And in this case, the only difference between the calculation is this is R/3 because there's 3 parallel guys, whereas this guy is R. Right, so that's the only difference, right? Okay, sorry I went late. That's it. If you have any questions when you're taking the quiz, let me know. It's the quiz questions are very similar. All right, talk to you guys later. Thanks.